Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello all, Roy Simpson here, Professor of Mathematics at Cosumnes River College in Sacramento, California. If you're watching this video, then I'm assuming that you've watched my video on geometric sequences and partial sums of geometric sequences. This is kind of a gateway into calculus and specifically a gateway into infinite summations of geometric sequences. Before we can get there though, we have to just stop over for a moment and talk about infinite series. And that's hard for me to avoid saying. I want to say series all the time because really in calculus, specifically Calc 2, you deal with them quite a bit. And sequences, while they're important and they're the basis of series, you don't deal with them as much. But infinite series, what is that? Well, any expression of the form summation k equals 1 to infinity, that's the difference here between a summation and a series, k equals 1 to infinity of a sub k, which is just the summation of a sequence, a1 plus a2 plus a3 forever. That is known as an infinite series, also known as just simply a series. So I will call it a series rather than an infinite series because you may have been able to tell I always trip over my words. So just being able to say series is nice. Also, turn off your Apple phone when I talk because it will want to constantly answer my questions because I say series quite a bit. Truthfully, infinite series are kind of the purview of Calc 2, but we have a special scenario in pre-calculus where we get to play with them. But before we get there, let's take a look at these. So let's write out a few terms of the following series. So the very first one is this beautiful summation n equals 1 to infinity of 1 over n, which is just equal to when n is 1, 1. When n is 2, 1/2. Increment when n is 3, 1/3. Increment when n is 4, 1/4, and so on and so forth. It goes on forever. Okay. The second one, summation k equals 1 to infinity, is this wonderful 1 over k minus 1 over k plus 1. This is a beautiful series. When k is equal to 1, I'll use actually different ink for this. So when k is equal to 1, I'll use blue for that. You get 1 minus 1/2. And then plus. When k is equal to 2, you have 1/2 minus 1/3. Plus. When k is equal to 3, you have 1/3 minus 1/4. When k is equal to 4, I ran out of colors here, I think. Yeah, I did. So I'll use black for this. You have 1/4 minus 1/5, and so on and so forth down the line. This is a very, very powerful series. We'll talk about more in a moment. You might notice something very special about it, but I'll leave it for you to notice, but I'm not going to tell you something about it. The next series, writing out a few terms here. Oh, you might also wonder, why didn't I just add up those fractions? Like, why didn't I write this as a half? And why didn't I write this as 1/6? And the reason why I don't do that is because of pattern recognition in mathematics. You often want to leave things kind of unsimplified initially, just so you can spy a pattern. And there is a pattern there. All right. So the next series is a -1 to the nth power over m. And that's a series from m equals 1 to infinity. Well, when m is equal to 1, I have -1 to the first, which is a -1 over 1. That's just a -1. Plus, when m is equal to 2, I have -1 squared, which is +1, over 2. When m is equal to 3, I have a -1 cubed, which is a -1 over 3, plus 1/4 minus 1/5, and so on and so forth. Now there's not really a beautiful compression that happens here, if that's what you noticed with the second example. But there's still something very beautiful about this. Notice, by the way, that this one we just did, the last one, number 3, I'll call it, is very similar to number 1. Number 1 and number 3 have a lot of similarities. They're both 1, 1/2, 1/3, 1/4. It's just one does this thing which we call an alternation. So this is an alternation. And that makes something very special about this. I also should note, for those who are fans of names, that this first one is called a harmonic series. Harmonic series. And the last one is called an alternating harmonic series. And I have my Calculus 2 students review series and sequences prior to a certain point in Calc 2. And so they may have already seen this in their class. Maybe, maybe not. By the way, this one is called a telescoping series. You don't need to know that, but it's nice to kind of name these. Now, just be honest, we'll come back to these in a moment. Before we do, I'd like to lay down a definition here. Convergent and divergent series. So let S sub n be the nth partial sum of the sequence A sub k, right? So you're summing up the first 10 values of a sequence or something like that. All right, and that's the sum of the first n terms of an infinite series. Actually, it's the first n terms of a sequence, but whatever. All right, and the infinite series that it's a partial sum for is the series going from 1 to infinity. So here we're not going from 1 to infinity, we're going from 1 to n, but we also have one that goes to infinity. This just is a smaller series, or smaller summation, I should say. Well, if you think about it, S sub n forms a sequence of values, right? So if I only wanted S sub 1, it would just be A1. If I only want S sub 2, it'd be A1 plus A2. If I only want S sub 3, it'd be A1 plus A2 plus A3, and so on and so forth down the line. So it provides us with a sequence of nth partial sums. And you could keep writing this sequence if you want to. It just goes on forever. Okay. And what we're going to do is we're going to say, hey, if that nth partial sum tends to S, and S is some finite number here. So as n goes to infinity, if S sub n approaches S, then we say that the series is convergent, or that it converges. And what do I mean by that? It means as I allow this n to go to infinity, as I allow that to go to infinity, if this approaches some finite value, then we say the series converges. So in other words, as we add more and more terms, if this becomes and locks down to a finite number, we can then say the series converges. Otherwise, we'd say the series diverges or is divergent. So let's go back and see how that works for our series that we were just writing out. And just to showcase for my students who have the lecture notes, I'm actually doing this example 12.3 number 9. I'm going to go to Desmos and go to those previous summations and showcase kind of whether or not they converge or diverge. These will not be proofs because you cannot prove something by just looking at a picture, but they will demonstrate whether something converges or diverges. So let's go ahead and do that. Now I want to note something here. All I did was search for Desmos series or sequences in series as well. And it brings up an applet that I'm going to play with here. The reason why I want to use somebody else's is because it's just much easier to use somebody else's code for this one. It's a little bit nicer. And I don't know if you recall, but our first series was the summation of 1 over n. And notice I'm using a capital N here. Okay. Now, in red, what you're seeing, well, maybe I should say it this way first. In blue, or purple, I guess that is. See, I'm kind of colorblind. So I turned off the red. In purple, what you're seeing are the values of the sequence. So when I plug in 1 just to the sequence, not the sum, but the sequence. So for the first term, its output is 1. The second term, its output is 1/2. The third term, its output is 1/3. And then I can allow this to go on forever and ever, right? At least to 100, because that's how this person has it coded. So what happens to the sums? Like if I want to add those terms, if I want to add 1 to 1/2, 1 and then add 1/2, what does the summation look like? Well, let's go ahead and I'll scroll down and turn on the summation. Well, here's the nth partial sum, s sub 1. In other words, this is the sum of the first term. This is the sum of the first two terms. It's 1 plus 1/2. Here's the sum of the first three terms, 1 plus 1/2 plus 1/3. Okay, so I hope you get the idea of what the red dots are. They are just summing up the first n terms of our given sequence. Now let's keep going here. I'm going to zoom out actually. We'll just keep going and keep going and keep going. Now, I don't know if I probably can actually change this. So I'm going to change this to 1,000 just to allow it to go to 1,000. And I will go ahead and zoom out even further. So I want to show you this sum looks to be continually growing, actually. Doesn't look to be stopping. I can kind of break Desmos if I go too quickly here. But it doesn't seem to be stopping. It'll grow and grow and grow. And eventually, actually, it will become whatever number we want it to. It'll grow to whatever we want. We call that growing without bound. So because the more terms that you add to the series, the larger it gets, it is a divergent series. Again, I want to drive that point home that this series, the harmonic series, is divergent, because when we've added the first term to the second term, it became 1.5, and then it became 1.833, and you add a quarter to that, and it's a little bit over 2, and whatever. But every time you add the next term, it just continually grows. Now, this is not the reason why it diverges, honestly. It's just that you're adding just enough in the next term to keep it growing fast enough to where it will not stop growing. Now, I'm going to tell you something magical from calculus here. If I had increased this power on this denominator here from 1 to maybe 1.1, that would actually converge. That would become finite. So I should say that the summation, the infinite sum there would become finite. So that's just a heads up that these series are very delicate. Minor adjustment to the sequence that the series is based upon can cause the series to converge or diverge. But in this case, the harmonic series is actually a divergent series. The second one, the telescoping series, let's go ahead and see what that looks like, because I think this is just an awesome series. All right, we're back here in the Desmos coded app here. And I don't know if you remember, but the series or the sequence that our series is based upon is 1 over n minus a 1 over n plus 1. It's capital N here. That's how this person has it coded. All right, so you can see, let me turn off the red. Let me just showcase the sequence itself. So the sequence, not the summation, but the sequence looks like the following. Notice how quickly it dives down to 0 versus my other sequence, which looked like that. Oh, I guess they both look like they dive down to 0 very quickly, don't they? Like, it looks like the terms of our sequence are really getting close to 0 very quickly. Right about here, it's 0.033. But if you take a look at the sequence that we are now dealing with, n plus 1, that's even closer to 0. It's 0.001 right there. So it gets close to 0 very quickly, which means that what we're adding as we move forward are very, very small numbers. Does that guarantee convergence? No, but there's something very special about this specific series. So let's turn on the summation. In fact, what I'm going to do is go ahead and reduce the n value here from 60 so that we can play. So we're going to see what happens when we start adding terms. That's the sum of the first one term of our entire sequence. Now we're summing 4 terms, 10 terms, 15 terms. Notice in this case, it does seem to level out. It doesn't seem to be growing very quickly. In fact, it looks like it really did level out, right? It's flatlining, which tells me if the sum is flatlining, that is probably converging to whatever it's flatlining to. Maybe a 0.99, maybe a 1. And that is actually true. It converges to 1. Now, this is not a proof, but this is a good, strong visualization. So over here, I'm just going to write down that it looks to be, that the telescoping series looks to be convergent. Now, the telescoping series has something very special about it. Notice that these middle values, -1/2, will cancel with that +1/2. And a -1/3 will cancel that +1/3. And that -1/4 will cancel the +1/4. And -1/5 will cancel the +1/5. And if you keep going forever, you're just, by the time you get to the very end, which there is no such thing, you're dealing with numbers that are basically like 0. And so the only survivor ends up being that 1. So it does converge to 1 when you add forever and ever and ever. You don't need to know that. That's a calculus concept, but really cool idea. Finally, let's go back to our 1/n situation, which is the harmonic series, but let's cause an alternation on it. So we're back here, and there's my 1/n, and I'll just put out a few terms. You can see that thing was just increasing. It was going without bound. But now, what if I put a -1 to the nth power on that? Rather than a 1, I put a parenthesis. You have to have a parenthesis. -1 raised to the nth power. Well, now this is interesting for a couple reasons. So I'm going to turn off the sequence. Actually, no, I'll leave the sequence on. So that's the sequence. That's the terms that you're adding up. And if you continue on forever, they look like they're bouncing around 0, a height of 0 there. Well, now let's turn that off because it's a little bit visually confusing. And let's turn on the sums. And notice the sums, the red dots are the sums, what it's summing to. And it looks like it's summing to around -2/3 or -0.7, something like that, right? If you keep going longer and longer and longer, let me go ahead and just have this go out a few more, 350 terms. So scroll over, you can see that it's just flatlining here, bouncing back and forth, -0.695, -0.692. So this is a very interesting alternating sequence, or alternating series in this case. So this one looks to be converging to some value. We don't know what it's converging to, but it looks to be converging to some value. So I'll say the same thing here. It looks to be convergent. And this is going to be, still writing here, there we go. And it is actually convergent. And that's what's weird about calculus, is that you have some things that are divergent. This guy right here diverges. If you add them up forever, it keeps growing. And then something very, very similar that actually converges. So calculus is a really interesting subject because you're dealing with infinities and the infinitesimal, and then you have something like this where you just have some weirdnesses happen. And you'll see that actually in a future video. I'm going to do something a couple videos from now that involves a little bit of calculus, but it's fun. So, all right. So this is an introduction, or this was, I suppose, an introduction to infinite series. In the next video, we're going to talk about infinite geometric series because we are in the middle of geometric sequences and series. So there we go.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Yes, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.